Okay, the next thing we want to tackle is our other tool for classifying critical values as local maximums or minimums. This one is going to rely on second derivatives instead of first derivatives. So let's just review a little bit about second derivatives in graphs. First one, if f double prime is greater than 0, we know that our function is concave up. So I'm going to fill this in out of order. But we can backpedal. The relationship between f prime and f double prime is a first derivative relationship. There's only one derivative between them. So f double prime is actually telling us about the slopes of f prime, which means positive f double prime implies increasing f prime. So another way to say concave up to yourself is your slopes are getting bigger. F prime is getting bigger. F prime is slope of f. So if slopes are increasing, your function is concave up. If f double prime is negative, then f prime is decreasing, and f is concave down. So another way to say concave down for yourself is that the slopes of the tangent lines are decreasing. That will make a concave down shape. We also know that if our function is continuous at some point x equals p and changes concavity at p, then f double prime either has to be 0 or undefined. It's kind of like critical values, but we're going f to f double prime instead of f to f prime. So then f double prime is 0 or undefined. If we then want to think about what is happening on f prime, so basically if f changes continuity, then f double prime changes signs. So it has to be 0 or undefined to change signs. And if f double prime changes signs, f prime changes directions, either switching from increasing to decreasing or decreasing to increasing, which means f prime has a local max or min, we'll say extrema. So there's either a max or min on your derivative, and your function, changing concavity, has an inflection point. So we already looked at these, but just to say it again, and maybe with a little bit more detail this time. Okay, so let's look at this graph, and you can absolutely try this one on your own. It's like your warm-up problem, but it's building up to this second derivative test, and then I'm going to go through it here as well. So we're supposed to estimate where we have critical values. I don't think my derivative is ever undefined. I don't see any vertical tangent lines. I don't see any sharp corners, no infinite oscillation. So we're only looking for when the derivative is 0, which would happen right here, somewhere around here, and right about here. So I'm thinking that one looks like it's pretty right on at x equals 2. The next one is maybe a little estimation needed. Maybe 5 1/4, 5.3, something like that. And then the last one looks like it's at 8.5 to me. So I have 3 critical values. This one also wants me to estimate inflection points, so that's some good review. I am seeing, let's color code it, definite concave down through this section of the graph. But somewhere along the way it switches because this is definitely concave up. And then it has to switch again because this is definitely concave down. So I'm thinking I have an inflection point somewhere around 3.5 and somewhere around 7. I think I drew mine something like 7.2. So maybe x is about 3.5 or 7.2. Okay, and then we want to identify which critical numbers are local maximums and minimums and think about what's going on with f double prime at these points. So this one is a max and a max and a min. At the maximums, both of them, the graph is concave down. And at the minimum, the graph is concave up. And this kind of makes sense to me because if you think about all of these are spots where the tangent line is horizontal. So if the graph bends down from a horizontal tangent line, that has to make this maximum shape. Same thing here. horizontal tangent line, if the graph bends down from that, concave down, it has to make that maximum shape. And at a horizontal tangent line, if the graph bends up, concave up, it has to make a minimum. Notice that we're not talking about when the derivative is undefined. So we'll do that in just a second, but this is specifically for when the derivative is 0. So I would say at the local max, f double prime is negative, and at the local min, f double prime is positive. Okay, I want to go back and look at that original graph we had that had some places where the derivative was undefined, so we can think about that really quick as well. So here is that first graph. The points that had f prime undefined were these. There's others, but I want to specifically look at the ones that were maximums and minimums. So the reason that we're not talking about maximums and minimums with second derivatives is because the derivative being undefined automatically means that the second derivative will also be undefined. So we can't get any concavity information at corners. It's impossible. So the second derivative test that we're about to build up is only good for flat spots. It's not good for corners, only for flat spots, because we can't talk about concavity at corners, but we can talk about concavity at flat spots. Okay, so let's put this all together. Down at the bottom, we have the second derivative test. And the second derivative test says that if the second derivative is continuous at a point, so this automatically means no corners, because if the derivative is undefined, the second derivative is also undefined, so no corners, only flat spots. And we know, again, this is emphasizing that same point, only flat spots. Then the second derivative can tell us whether we have a local maximum or minimum. So if the second derivative is positive, meaning the graph is concave up, then the function has to have a local minimum. If the graph is concave down, the graph has to have a local maximum. And again, key to this is you being able to visualize flat spot, bending up makes a minimum, flat spot, bending down makes a maximum. If the second derivative is also 0, the test fails. So the second derivative test isn't quite as reliable as the first derivative test, but in certain situations, it's way quicker and easier. In particular for polynomials, it's way quicker to take a second derivative and plug in a number than it is to build a whole first derivative sign chart. So this one is great for polynomials. We can use it on other things, and we will. I don't specify a lot in your homework whether you have to use a first or second derivative, but on skills tests I will, so just make sure you're prepared for either. Often I get students that are ready for their first derivative test, but maybe didn't really practice their second derivative test. So make sure you're bouncing back and forth. You can even do a couple of them both ways and make sure your answers agree. So to do a second derivative test, you'll find critical values. You will then find a second derivative. So critical values are f prime equals 0. And if f prime is undefined, you exit out and you go back to a first derivative test. So find critical values where f prime equals 0. Find f double prime and plug in critical values. So you're not making a sign chart. You actually want to know right at the critical value what is the concavity. And that will give you your final conclusion. Okay, I'm going to cut this here and then we will do an example.